Welcome to the deep dive. Today, we're jumping into something really fascinating about the Gaia mission.
Yeah, something maybe a bit less talked about than its main job.
Exactly. We all know Gaia maps, like over a billion stars, right?
Yeah.
Pinpointing where they are, how they move. That's the astrometry.
Mind-boggling precision, yeah.
But at the exact same time, it's collecting incredibly accurate photometry, basically measuring star brightness in different colors.
And that's what we're focusing on. Think of this as your shortcut to understanding why this color stuff from space is, well, a really big deal in astronomy today.
Right, because you can measure star brightness from Earth. So the big question is, why bother doing it up there on Gaia?
Well, there are some really compelling reasons, both instrumental and scientific.
Okay.
And that's our mission for this deep dive, to unpack why Gaia's onboard photometry is so critical and what it tells us about all those stars.
All right, let's get into it. The instrumental reasons first. Why is it essential for the telescope itself?
Okay, so think about any high-precision telescope, even one as amazing as Gaia's. It's not perfectly perfect. There are tiny flaws.
Uh-huh.
These can cause something called chromatic displacement. Basically, a star's measured position might seem to shift just a tiny bit depending on its color. Red light focuses slightly differently than blue light, you know.
Ah, okay. Like needing the right glasses prescription.
Exactly. To get Gaia's ultra-sharp star positions, you absolutely have to know the star's color to correct for that tiny shift. The onboard photometry gives you that color info right then and there.
So without the color data, the astrometry, the position measurements, they'd be slightly fuzzy.
Precisely. Color is key for Gaia's sharp vision. It's fundamentally baked into getting those accurate positions.
Wow, okay. So it's not just bonus science, it's vital for the core mission. But you mentioned scientific reasons, too.
Absolutely. I mean, the universe isn't static, right? Stars change, they pulse, they flare up, their brightness varies.
Yeah, variable stars.
Right. So for Gaia to do an unbiased survey, meaning it doesn't just accidentally pick out stars that happen to be bright when Gaia looks, it needs to base its selection on how bright a star is at that exact moment it's being measured.
Oh, I see. So it doesn't just catch the flashy ones, it gets a fair sample.
Exactly. It needs that simultaneous onboard photometry to make that happen. It ensures a true census, not skewed by variability.
Makes sense.
And there's a bit more on the statistical side, too. To really analyze billions of stars properly, you need to select them based on detection and brightness thresholds, using the same kind of resolution, the same angular detail as the position measurements.
Keeping everything consistent.
Yeah. Having the photometry integrated right there ensures that consistency. It's all about the integrity of the massive data set.
Okay, that covered the steady stars, or
Yeah.
even the slowly varying ones. What about things that happen fast?
Good point. Think about transients. Supernovae, for example. They appear suddenly, then fade.
Right. Blink and you miss them sometimes?
Or even things in our own solar system, like asteroids whizzing by. They move quickly against the background stars. For these, having Gaia constantly scanning and measuring brightness with its onboard system is, well, invaluable.
It can catch these fleeting events.
Yes, events that ground-based surveys, which might only look at a patch of sky now and then, could easily miss. Gaia provides this continuous monitoring across the whole sky.
Okay, sold. Onboard photometry is clearly essential. So, how did they end up with the system Gaia has now? I heard the initial ideas were quite different.
Oh, definitely. There was quite an evolution. Gaia's predecessor, Hipparchus, it only had two-color photometry, very basic,
It's
really.
the two broad color bands.
Yeah. For Gaia, the ambition was much, much higher. The goal was to get enough color information to figure out a star's basic type, its temperature, essentially, but also its size, whether it's a giant or a dwarf, its chemical makeup, what we call metallicity.
And how much dust is dimming its light?
Extinction. All of that.
Yeah.
To paint a really detailed picture of every single star.
So, much richer data needed. How were they planning to get that initially?
Well, they had to weigh up a lot of things, like
Yeah.
how many different color filters do we need? Where do they go in the focal plane? Do we measure every star and every filter every time?
And how do you split the time? Because the star only passes across the view for a short period.
Exactly. How much time for the super precise position measurements and how much for the color measurements? It was a complex trade-off. Scientific desire versus engineering reality.
Sounds like a tough puzzle. What kind of filter numbers were they thinking about?
The science case was huge. With distances for 1 billion stars, you could suddenly do incredible things. Studying stars at every stage of life, from birth to death, different types of variable stars, stars eclipsing each other in binary systems.
Even asteroids in our solar system.
Tens of thousands of them. Their colors tell you about their composition. So all this science was pushing for a really sophisticated multicolor system.
A broad demand, then. Were there key people driving this?
Oh yes, the photometry working group was central. Co-led by Eric Hug and Carmi Jordy, they brought in experts like Jens Nude, who knew the Strömgren system well, that's great for hot stars, and Vitas Strazis, a champion of the Stromville system, which is really good for classifying all sorts of stars, even when their light is reddened by dust.
So, building on existing, proven techniques, how did these ideas become hardware designs?
Well, it evolved. Around 1998, one idea was 4 broad filters on the main telescopes, plus 7 medium ones on a separate, smaller telescope.
A dedicated photometry scope.
Yeah, then by 2000, it was maybe 11 intermediate filters. By 2006, the plan got really ambitious, 19 different filters.
19, wow. That's incredibly detailed color information.
It would have been, relying on traditional filters placed in the light path.
So, what changed? You mentioned a dramatic change.
Right. Well, engineering and cost often step in. While the scientists were literally finalizing the paper on the 19-filter system, the company bidding to build Gaia Matra Marconi Space, who won the contract, came up with a radically different idea.
During the bidding. So it was kept quiet initially.
Exactly. It was part of their competitive proposal.
Okay, I'm intrigued. What was the big idea?
Their concept was, well, get rid of the dedicated photometry telescope entirely and replace all those filters with just 2 simple low dispersion prisms.
Prisms, like in a basic spectroscope, instead of filters.
Sort of, yes. The main drivers were simplifying operations, cutting down mass, and saving money. It was a bold move.
How did they make that work? Filters give you distinct brightnesses and specific color ranges. Prisms spread light out.
Through a lot of clever work. Key scientists got heavily involved, running tons of simulations to optimize the prism properties. It was a novel approach, but they figured out how to make it deliver the goods.
So the prisms ended up being the final design.
Yes, that's the system Gaia flies with today. There's one big focal plane assembly for both telescopes doing 5 jobs at once. Finding stars, measuring positions, getting color info via the blue photometer BP and red photometer RP prisms, measuring radial velocity for brighter stars, and even checking the telescope's shape.
All in one. That's efficient.
Incredibly efficient. And they managed to get richness in color information similar to that complex filter system, but with a much simpler, more robust design.
So the same light hitting the detectors for position is also used for color, just processed differently.
Exactly. And the main astrometric detectors themselves provide what's called the G-band. That's basically unfiltered white light covering a huge wavelength range from ultraviolet to near infrared.
Wide open.
Yep. So it collects the most light overall, giving the best signal to noise. That makes the G-band really good for studying stars that very quickly.
Okay, so G-band is the overall brightness. How did the 2 prisms deliver the multicolor part?
Right. These 2 prisms, made of fused silica, sit in the light path just before the main detectors. And like any prism, they disperse the light, they spread it out into a little spectrum for each star.
A mini rainbow, like you said earlier.
Pretty much. A very short, low-resolution spectrum. The effective color bands we get aren't defined by filters anymore, but by a mix of things. Coatings on the prisms, how well the telescope mirrors transmit different colors, and how sensitive the detectors are to different wavelengths.
So it's not discrete measurements anymore, but a continuous spread of light.
Exactly. A continuous low-resolution spectrum. Each prism, BP for blue and RP for red, has its own dedicated strip of CCD detectors. As the star's image sweeps across these strips, its light gets spread out along the scan direction.
How much spread?
For a typical star, maybe across 45 pixels or so, the detectors read out a little window around the star spectrum, capturing the star's light and the nearby sky background at the same time.
And the blue and red prisms spread the light differently.
Yes, that's key. The blue photometer, BP, covers roughly 330 to 680 nanometers. The dispersion, how much it spreads the light, varies across that range.
More spread at some colors than others.
Yeah. From about 3 nanometers per pixel up to 27. The red photometer, RP, goes from 640 to 10,050 nanometers, with its dispersion varying from 7 to 15 nanometers per pixel.
Why the different dispersions?
It was cleverly engineered. The whole setup, the wavelength coverage, and the effective resolution you get from the spreading was designed to roughly mimic what that original 19 filter system would have delivered.
That is clever, getting similar results with simpler hardware. So what happens to the signal from those spread out spectra on the detectors?
For most stars, the vast majority of the signal across the spectrum, perpendicular to the scan direction, gets added together, or bin, right on the chip. This gives a one-dimensional spectrum for each star pass.
Just a line of brightness values at different effective wavelengths?
Sort of, yes. Only for the really bright stars, brighter than G magnitude 11.5 or so, do they read out the full unbinned 2D image patch. That gives finer detail for those specific objects.
Okay, this must generate a huge amount of data, especially in crowded areas like the Milky Way Center. Don't these little spectra overlap?
Ah, yes. That's a big challenge. Gaia's main position measurements can handle incredibly dense fields, maybe 1 million stars per square degree. But the dispersed BPRP spectra start to overlap significantly much sooner, maybe around 750,000 stars per square degree.
The photometry gets limited in dense regions.
It can be, yeah. The spectra can get cut off, or fainter stars might get missed because the system prioritizes brighter ones when things get crowded. But the data processing teams are incredibly smart.
They have workarounds.
They've developed really sophisticated methods specifically for scientifically vital crowded regions like Bade's window near the galactic center or the Omega Centauri star cluster. They can disentangle a lot more information than you might think, even there.
Amazing, pushing the limits. So once this flood of raw data positions, G-band, BPRP spectra gets down to Earth, what's the pipeline?
It's a massive, dedicated photometric pipeline. It takes data from the SkyMapper detectors, which first detect the stars, the main astrometric detectors, and the BPRP detectors.
It puts it all together.
It calibrates the G-band fluxes from the astrometry to create what we call epoch photometry, basically, a list of brightness measurements over time for each star in the G-band.
Like curve in G.
Exactly. And then it takes the total light measured in the BP spectrum and the RP spectrum for each observation and calibrates those to create epoch photometry in 2 derived bands, GBP and GRP.
So integrated blue and red brightnesses over time as well.
Yes. But crucially, it also calibrates the BP and RP spectra themselves. Both wavelength calibration, knowing exactly which wavelength corresponds to which pixel, and flux calibration, knowing the true brightness at each wavelength.
How on earth do they calibrate that accurately? Billions of stars, changing instruments.
With standard stars, they observe a special set of stars whose light properties, their brightness across all colors, have been measured extremely precisely and reliably using big telescopes on the ground.
So known references scattered across the sky.
Exactly. And they run extensive monitoring campaigns, constantly re-observing these standard stars throughout the mission to track any tiny changes in Gaia's instruments and keep the calibration rock solid. They're like calibration beacons.
Right, like reference points. So where are we now with the data releases? How much of this photometric data is actually available?
Well, the latest big release, EDR3, Early Data Release 3, it's already phenomenal. It has G-band photometry for, get this, 1.806 billion sources.
Billion with a B.
And GRP bands for 1.540 billion of those.
Incredible numbers. How precise are these measurements?
For G-band, the median uncertainty is tiny for reasonably bright stars, like 0.2 millimagnitudes, that's 0.0002 magnitudes, for stars between 10th and 14th mag. Even down at 19th magnitude, it's still around 2.6 millimagnitudes. Extremely precise.
That level of precision for over 1 billion stars, it's just staggering. What kind of science is this enabling? What are people doing with it?
Well, the downstream processing is where it gets really exciting. First, those light curves, over time, the epoch photometry in G, GBP, and GRP are fed into variable star analysis pipelines.
Finding and classifying stars that change brightness.
Exactly. Identifying different types of variability, characterizing their light curves, finding new pulsating stars, eclipsing binaries. It's a treasure trove for variability studies.
Uncovering the dynamics of the galaxy stars.
Absolutely. And then there's what's called astrophysical parameter inference. This is where you combine everything Gaia measures.
Position, motion, colors.
Yes, the astrometry, the multicolor photometry from BPRP, and for brighter stars, the spectra from the radial velocity spectrometer, the RVS. Putting it all together lets scientists classify sources, figuring out if something is a normal star, a white dwarf, a binary system, a distant quasar, or even a whole galaxy.
Going beyond just detection to identification.
And then, crucially, inferring their physical properties. What are these things actually like?
Okay, so what properties can you get just from the BP and RP photometry, those low-res spectra?
They are surprisingly powerful. From BP and RP, you can estimate several key stellar parameters. Things like the star's effective temperature, how hot it is, its surface gravity related to its size and mass.
Like giant versus dwarfs.
Exactly. Also, its metallicity, the overall abundance of heavy elements. And that interstellar extinction, we talked about how much dust is blocking the light.
Wow, all from those simple prism spectra.
Primarily, yes. For brighter stars, the RVS spectra add more detail, like abundances of specific elements, but BPRP gives you these fundamental parameters for well over 1 billion stars.
How accurate are these derived parameters? Can we really trust the temperature of a star billions of light years away based on this?
The accuracy is pretty impressive, though it depends on brightness and how much dust is in the way. For, say, typical sun-like stars, FGKM types around 15th magnitude with low extinction,
Yeah.
you can typically estimate temperature with an uncertainty of maybe 75 to 250 Kelvin, extinction within maybe 0.06 to 0.15 magnitudes, surface gravity within zero point 0.2 to zero point 0.5 dex, that's a log scale, and metallicity within zero point 0.1 to zero point 0.3 dex.
That's pretty specific information for so many stars.
It is, though you have to be careful. There are still some challenges, what we call degeneracies. Sometimes a cooler star with less dust can look very similar in color to a hotter star that's more reddened by dust.
So temperature and extinction can be tricky to separate sometimes.
Exactly. It requires careful analysis, often bringing in the distance information from the astrometry helps break those degeneracies.
Even with those caveats, it's just an incredible data set. It's really clear now how this photometry isn't just an add-on, it's fundamental to Gaia.
Absolutely. That onboard multicolor photometry, achieved with that clever prism design, it's a cornerstone of the whole mission. It's providing essential, fundamental data on the nature, the physics, of over 1 billion stars, way beyond just where they are and how they're moving.
So by carefully measuring the colors, the light signatures of all these stars, Gaia is unlocking secrets about how stars evolve, the huge variety of variable stars, objects in our own solar system, and really the whole structure and history of the Milky Way.
Couldn't have said it better myself. It's transforming our view of the galaxy.
It really makes you think, doesn't it? If this is what Gaia's tachometry can do, what might future missions achieve with even more advanced ways to measure starlight? What big questions are out there that just need slightly more precise, slightly more detailed measurements of light to crack them open?
That is the fascinating question, isn't it? What cosmic secrets are still hidden in the subtle variations of light, just waiting for the right instrument, the right technique to bring them into focus? It's an ongoing journey.